M.Sc Physics online lecture series for the subject Physics of Nanomaterials. This is second semester subject which has code PHOTB4. In last lecture we have discussed that the nanoscience, to understand nanoscience we need to understand the quantum mechanics and its basic properties. At the small scale, the laws of classical mechanics or Newtonian mechanics are not able to describe the exact situation of the particle. Okay, for that case we use quantum mechanics to represent or to find the particular properties of that particle. Last lecture we have studied that the time dependent Schrödinger equation is that h cross square by minus h cross square by twice n double 2 psi by double x square in one dimension, which is x comma t, plus v of x comma t psi of x comma t is equal to I h cross gamma psi of x comma t by gamma t, and the time independent Schrödinger equation is like minus h cross square by twice n d2 psi by dx cube d2 psi by dx square plus v of x psi of x is equal to t psi of x. This is time independent Schrödinger equation and this is time dependent Schrödinger equation. But here the energy is equal to h cross square k square by twice n. Okay. Now in today's lecture we are discussing the electron confinement for the nano science. Right. So let's begin with the electron confinement of nanomaterials. Okay, so electron confinement. What does this mean, that the electron confinement? Confinement means restriction to the particular particle, right? So there is a three types of electron confinement. Okay, so first one is confinement in one direction. Okay, so this means that freedom of particle in two dimension. Okay, get it? If the confinement in one direction, there is restriction in only one direction, then for that particle there is a freedom in two dimension, or you can move in two dimension. Second one is confinement in two dimensions or in two directions. So the particle cannot move in two directions. So this case represent particle has freedom in only I can say here confinement in one dimension and the freedom of particle in two directions. Okay, so confinement in two dimension, freedom in one direction only, right? And the third one, is that confinement in, first one is confinement in one dimension, second one is confinement in two dimension, the third one is for confinement in all dimension. That is, there is no freedom for the particle. Okay, so there are these three conditions. In nanoscience, we are going to discuss each condition in detail. Okay, how these confinements are directly related to the nanoscience is that the confinement of particle in one dimension represent that the freedom of particle in two dimension, that is, the particle move only in two dimension, right? You can say that only x axis and y axis. If we elaborate this, we can think of the thin films. Okay, so the examples of this is for thin films. Okay, so when we study about confinement in one dimension, we actually study about thin films. And the second, confinement in two dimension, that is freedom in one direction only. So for this case, we study about nanowires, right? Wires are extended only in one direction. Okay, but what about this confinement in all dimensions, that is, there is no freedom for the particle. This particle has no extended in space. So this has an example known as quantum dots, right? Dot. It is not extended along x direction, y direction, and z direction. Okay, this is also called as what? Nano particles, right? Nanoparticles, nanowires, and thin films. Okay, to explain this concept, we use some standard points in quantum mechanics. It is like we use the term as particle in a box in 1D, 2D, and 3D. Okay, so quantum mechanics concept, the particle in a box in 2D, 2D, and 3D gives us the explanation about confinement of electron in one dimension, two dimension, and three dimension. So let's begin with electron confinement in one dimension. Electron confinement in one dimension, that explains the quantum concept of particle in a box for one dimension. So let's consider that the particle in one dimensional box, right? For that, we consider consider the potential energy as potential is time independent. I have explained in the last lecture how the potential is time independent at the scale of nano. Okay, we have x is 0 in the region, for the region where x varies from 0 to a is the length of box, and it is infinity for x is greater than a and x is less than a. This much potential we have given for the one-dimensional box, particle in one-dimensional box. The potential given for one particle in one-dimensional box is that the potential is 0 in region between 0 to a, and it is infinity at a region greater than x is greater than a and x is less than 0. You can draw it like this. This is x-axis, this is for potential v of x. So this is 0 and the box length is at a. Okay, so to draw this outside the box, the potential is infinity, and inside the potential is 0. That is, between the region 0 and a, the potential is 0, and outside the region, that is x is greater than a and x is less than 0, the potential is at infinity. Okay, to get the different energy states for this condition, we use the time independent coordinate equation is right for in one dimension, that is in 1D, because we are saying particle in one dimensional box, which can be written as minus h cross square by pi cell. As it is in one dimension, the wave function psi is only depend on x variable, so we write total derivative, that is d2 psi of x by dx square, no partial derivative, that is delta. We write here total derivative, and the potential v of x, which is time independent, and the wave function psi of x, finally on RHS it is e psi of x. Okay, this m represents the mass of that particle. Okay, to after solving this coordinate equation, we get the wave function. Okay, and if there are some properties of wave function, we will discuss them shortly. Okay, and after using boundary conditions, these are called the boundary conditions. The equation 1 as solution as psi of x is equal to a sin of 2me by h cut x is whole in under root and h cut square, this whole is angle cosine, and next one is for b cos of twice me by h cut square 1 by 2 x. Okay, this is the solution for this Schrodinger, time independent Schrodinger equation for one dimensional potential valve or one dimensional potential box. Okay. So using boundary condition is that at x equal to 0, that psi of 0 is 0, right? So at the ends or at the boundary points at x equal to 0 and x equal to a, the wave function psi of 0 is 0, which implies that when we put this in equation 2 gives us that the quantity when we put x equal to 0, the term x equal to 0 over here, this term becomes 0. Okay, and when we put x equal to 0 over here, cos 0 is 1, so we are left with b is equal to 0 because psi of 0 is 0. This term will become 0 and cos of 0 becomes 1, so we are left with b into 1, which is 1, and b into 1 is b, and b is equal to 0. Okay, when you put this value of b into the equation 2, in equation 2, we get that psi of x is equal to a sin of twice m a by h cross square bracket is 1 by 2 x. Okay, and when we put using second boundary condition, which is at x equal to a, the psi of a is also 0. So the equation 3 becomes as psi of a is equal to a sin of twice ma by h cross square 1 by 2, in place of x it is a. Okay, and psi of a is 0, so 0 is equal to a sin of twice ma by h cross square 1 by 2 a. As you can see that the term quantity with the constants a and b, if b is 0, a is not equal to 0, or if a is 0, b is not equal to 0. For this case, we got that b is equal to 0. So we say that, but a cannot be 0. So the resultant quantity, which is 0, is twice m e by cross square 1 by 2 a. This quantity becomes or should be 0 if a is not equal to 0, because there are two terms, a into sin of this much. So if a is not 0, the sin should be 0. The sin twice m by h cross square raised to 1 by 2 a is 0. And this condition holds true when sin of n pi is 0. When we put sin of n pi, the integral multiple of pi, the sin of all the integral multiple of pi gives us 0. So we can put that this value, that twice me by h cross square bracket raised to 1 by 2 a, this must be n pi. Then and only then the sign of this quantity is equal to 0. Right? Now we say that the twice me by h cross square bracket to 1 by 2 a is equal to n pi. In this case, where n has values as n equal to 1, 2, 3, 4 and so on. But there is a special case of n is not equal to 0. Okay, why we are not using n is not equal to 0? Because we have seen that at the boundary conditions that the particle must be present inside the potential wave. If we use that n equal to 0, the whole equation becomes 0. Okay, for n equal to 0. So that represents that the potential of the particle is not present inside the wave, but that is not the physical condition. Okay, so that we are not using the value of n is not equal to 0. Okay, now if we resolve this equation number 4 by rearranging equation 4 as on squaring both sides, we get twice me by h cross square. This under root square goes out, a square is equal to m square pi square. For energy, if we calculate for energy, we get m square pi square, the denominator goes to numerator, h cross square by this numerator twice m a square. From this, we conclude that the pi value is constant, h value is constant, h cross is what? H cross is equal to h by 2 pi, right? So h is Planck's constant, right? So that is also constant. 2 is constant, m is what? Mass of that particle. Generally we are discussing for electron. So m is for mass of electron, and a is constant, which is the distance of the length of this box. Okay, so we can see that the energy E is directly proportional to the integral n, which is n square. Okay, so from this n we can say that the energy is directly proportional to n square. When we put the values of n as 1, 2, 3, 4 or negative values of that -1, -2, -3, we take its square and that becomes positive. So from this relation we conclude that the energy is quantized for the given one-dimensional potential wave or potential box, right? So if we confinement of electron in one dimension, we get energy of that nanoparticle or the electron is directly proportional to n square. Okay, with the wave function psi of x is equal to a sine of twice me by cross square 1 by 2 x, right? You can determine this constant by normalizing condition by using normalization condition. We can find the value for a. Okay, and that normalization condition, when we integrate from -infinity to +infinity, the mod psi square over dx for one dimension is equal to 1. This gives us a value as 2 under root 2 by a. Okay, so final wave function sin of x can be written as 2 by a sin of, when we put the value of energy in this equation, so we are going to get n pi by a into x. Okay, using the value of e, that n square pi square h cross square by twice ma square putting in this equation, we are left with n pi by a into x. So this gives us the wave function for that particle, which determines the position or the properties of that particle and this energy of that respective particle. From these results, we conclude some standard properties for nanomaterials in one dimension or nanoparticles in one dimension. So let's see, these are the properties. What are those? This says that if we determine the wave function, it says that there may be a number of wave functions satisfying Schrodinger equation, but all may not be able to describe the given situation. Okay, then the acceptable wave function should satisfy the physical boundary condition. So what are the physical boundary conditions? Let's discuss. Okay, in this image we can see that the physical boundary conditions are: it is necessary that the psi should be well behaved function and satisfy following condition. The first condition is the psi must be finite and had a single value at all points over the Cartesian coordinate. Okay, or you can say over the space, coordinate space. Second condition is that it should be continuous at all points of the coordinate space. And third condition, the derivative of psi. Okay, if we are using in 3 dimensions, then the derivative of psi, which is da by psi by da by x, da by psi by da by y, and the da by psi by da by z, must be continuous or also be continuous. So we have studied in today's lecture the one-dimensional potential wave, the potential given in particular boundary conditions, and using time-independent Schrodinger equation in one dimension, we have found that its respective energy and the wave function value. Okay, or in the next lecture we start with density of states for the nanomaterials.